Welcome to The Deep Dive. Today, we're looking at something that feels like a really major step forward in edge computing.
It really is.
We're talking about how these huge, powerful vision language models, VLMs, can finally be fine-tuned right on your small devices.
Right on your phone, yeah. Our mission here is to unpack a new approach from some Amazon researchers called SharpZO.
Which they presented at NeurIPS 2025.
Exactly. For years, you had this brutal trade-off, High performance meant huge memory, low memory meant, well, terrible accuracy.
And SharpZO claims to solve that. So we're not talking about the cloud anymore. This is high-performance AI getting an upgrade right there on your device.
That's the goal.
But let's start with the big hurdle. I mean, why is it so hard to update these models on a phone in the first place?
It all comes down to the standard way these models learn. It's a process called backpropagation.
Right, where it moves backwards from an error to figure out how to learn.
Exactly. And to do that, it has to store every single intermediate step along the way. And that process is it's an absolute memory hog.
So for a device with limited RAM, it's a complete non-starter.
A total non-starter. It just can't handle it.
Okay, so that's why the industry started looking at zeroth order estimation, or ZEO.
Right, ZO for short. It only uses forward passes, so it's way, way lighter on memory and computation.
But the accuracy is known to be awful, isn't it? So that seems like a massive trade-off.
It is a massive trade-off, and that's the whole reason SharpZO even exists. The problem with existing ZO methods is extremely high variance in the gradients it estimates.
Okay,
To really get it, you have to think about the model's loss landscape.
And this is a great metaphor. It's like a map of all the possible errors. Right?
Exactly.
Yeah.
And the bottom of the deepest valley on that map.
Yeah.
That's your perfect model.
Okay.
But with all that noise, that high variance from ZO, the model sees that map as incredibly jagged, really sharp.
So instead of smoothly rolling downhill into the best solution,
It gets stuck. It just bounces around in these shallow, suboptimal dips. It never finds the real deep valley.
that makes perfect sense. So the model is basically paralyzed by all that noise. The challenge then is to smooth out that map.
That's the entire game.
So how does SharpZO's two-stage hybrid approach actually manage to do that?
It's a really smart sort of two-pronged attack. Stage one is what they call global exploration.
Global exploration.
Yeah, you can think of it like a digital bulldozer. It uses this evolutionary strategy to actively smooth out the landscape it sees.
It builds a better starting point.
A much better one. And the critical part is that this strategy accounts for the worst possible loss nearby, which is what really helps it minimize those sharp edges.
Okay, so stage one prepares the ground, finds a smooth path. Then stage two, local search, takes over.
Precisely. The second stage uses a modified ZO algorithm that's built for refinement. It tackles the high variance by essentially suppressing those noisy outlier estimates.
It just cleans up the data.
It normalizes the gradient vector so
Yeah.
the model can finally take these clean, refined steps toward the true optimal.
All right, let's get to the bottom line, because this is where it gets really exciting. The results. SharpZO improved accuracy by up to 7% over other forward-only methods like ZIP and BlackVIP.
It did. And what's really impressive to me is that its accuracy gets very close to COOP.
And COOP is a traditional backpropagation method, right? Well, the memory-hungry one we said was a non-starter.
That's the one. So it's competing with the heavyweights while using a fraction of the resources
Oh, yeah.
and the speed. Well, the speed is just staggering.
Okay, tell me about that.
On the ImageNet dataset, SharpZO reached the target accuracy in just about 15 minutes.
15. And the baseline, BlackVIP, took what?
170 minutes. 170.
Wow. Okay, so that's not just an improve. That fundamentally changes what's actually possible for deployment.
It really does. And we saw it was more robust, too. It performed better on out-of-distribution data like ImageNet Sketch.
So my smart glasses could learn my specific routines without ever sending my data to a server.
That's the promise. Now, we should be clear. The current scope here is something called prompt tuning.
Which is a form of parameter-efficient fine-tuning, or PEFT.
Exactly. So the number of parameters it's actually training is intentionally small right now. That makes it a perfect fit for the edge.
So wrapping this up, what's the big takeaway? This tech is proving that high accuracy on-device fine-tuning is actually achievable.
Right. We're decoupling high performance from high memory.
So efficiency and power are no longer mutually exclusive on your devices.
They don't have to be, no.
Okay, so here's the final thought I want to leave everyone with. The researchers acknowledge that scaling this beyond just prompt tuning is the next big challenge.
A huge challenge for sure.
But if they can do it, if this approach can be scaled up, How dramatically does that change the very definition of what a smart device can do all by itself?
Well, you're opening the door to truly personalized, always learning AI that never has to phone home for an update. Your device just becomes inherently more powerful and, a lot more private.